We got everybody here who's coming, I guess. But I see somebody who isn't here. How do you like that? Now, that's an old philosophical question, isn't it?
Right.
Whether you can see somebody that isn't here. I remember arguing in Princeton with the graduate students for hours and hours, the philosophy students, as to whether what you were talking about when you said there was no chicken in the icebox. Yeah, well, it's philosophy.
So much for you. You outgrew that phase.
That's why, yeah, I have nothing to do with philosophers ever since. We thought that it was possible that there's still people who don't appreciate the difficulty of this thing with the boxes, and so we'd like to divide you into two groups. Those who are perfectly confident about it and don't want me to go over it 16 more times, and those who would like me to go over it, well, at least 2 more times. So can we, we're going to divide this thing up, and we'd like to know how many want me to go over it a couple more times till they really fully feel the difficulty. All right, we have 2, 3 customers, something like that. So what we'll do is that Ralph over there, who's an expert and my assistant guru, will take care of you. In the meantime, the guys who've been asking me very technical questions about perturbation theory, calculations, and other matters of this kind will have a chance to talk to me. Because we have such a difference in the backgrounds of people, we're going to separate temporarily. So the ones who are having trouble before will catch up and see why it's interesting, because that's the whole purpose of this, is to understand that. If you don't understand that, we're not going to understand anything else. I mean, there's no problems. So that's the essential thing. After that, it's very easy. It's going to be easier. It's just like climbing a mountain, and from then on, it's to get a view. You see the view, and now you climb around down on the ground and have fun. So that's what it is. But we have to get you up to the mountain, right? So Ralph will help you climb to the top of the mountain. In the meantime, these guys who think they're there already will waste time by answering the technical things and complicated things, so which the others won't be interested in anyway. All right? So can we do it that way? So he's over there.
I'd like to just, go out to the tape side.
All right. How about that? So those who are having, you're not going to miss anything, in other words, because it's just going to be some.
Specifically the problem with 2/3, why is 2/3 so
Yeah. So we'll just take care of that, and the other ones will be. We'll talk about other things, please. Then I'll come back when they're all back, all on the mountain. Then we'll go back to the top of the mountain and show what the views are from there on, okay? So the present questions would perhaps be best if they're not directly attached to this question of the 2/3. We'll delay those until our friends come back from the mountain, okay?
Brownian motion.
Oh, Brownian motion. That, of course, is fun. It's you mean, what do you want me to do about it? You know about it?
I know a little bit about it, and I was thinking in terms of what you said yesterday about, well, the reason it came up to mind was you said, well, the atom doesn't have to act the way we act.
Yes.
On a side because of different scale. And then I was thinking, well, where would randomness be in the cell? And I was thinking of diffusion.
Living cells, you mean?
In
Yeah,
in terms
right.
of biological process, I was
Right.
thinking of diffusion.
Right.
And I reformulated the question of that by saying, talk about Brownian motion.
Yes, there's a kind of randomness, but that randomness is not involved in quantum mechanical randomness. You're quite aware. And it's due to the complexity of things, that there's so much stuff and the atoms are bouncing against each other in a kind of chaotic manner, so that for example, a liquid like water, the molecules are, we can take a normal view of molecules as little balls or little shapes of different kinds, and all the same kind, actually. They're all water molecules. And that they're piled together and jiggling all the time next to each other. And this perpetual jiggling is molecular motion. Brownian motion is observable. So it's possible to see this jiggling if you put a small particle, very fine particle of dirt. As a matter of fact, I did it with toothpaste. It's rather nice with toothpaste. If you haven't got a very powerful good microscope, it's easy to see. If you put something like toothpaste or something that's a little powder in it, then the very fine particles keep jiggling about all the time under the microscope perpetually. In the case of the toothpaste, they are flat the one that I happened to have, were very good because they were some kind of flat little crystals. And my microscope wasn't even big enough to see them. But because they would turn and the light would come just right, it would reflect. And there'd be these little flashes all over. So it was kind of, but it's easy with a good microscope. And it's very much like, I haven't seen this for years, but there used to be sometimes tremendous push balls that they had, enormous ball, great big thing, and they put it on a field with people trying to push it to some direction, the other team is trying to push it the other way, and the whole ball moves, and there's this crowd of people underneath, all pushing one way or the other, and the ball just jiggles. And if you look at it from a distance, you could imagine it was so far away you couldn't see the individual people, but could still make out the little ball. And you'd see this little ball jiggling, from which you can infer that the people are jiggling. So in the same way, what you're looking at is a very large mass of atoms when you look at a particle that you can see, because a particle you can see even in a microscope is a billion atoms or so. It's a great big thing. But it doesn't stay put because it's being bombarded all this time by the little atoms, and it therefore jiggles a little bit, and that's called Brownian motion. It was discovered by Robert Brown, a biologist, that when he looked through a microscope, he saw this jiggling motion. And being a biologist, you would think that he would decide that this motion that he saw must be a form of life. But he was a good biologist and made the necessary experiments and ultimately discovered that the motion even existed in the water that was enclosed in a quartz crystal that you could get from the ground that had been there for millions and millions of years. And he looked in, it was still jiggling inside there, so he concluded that couldn't be life, that was a universal phenomenon of nature, and it is, that we look very calm, we look at things, they're permanent, they're stationary, but as a matter of fact, of course, they're made out of piles of atoms which are always jiggling. Our eyes can't see the delicate jiggling, but that is a way that you could make a random generator. You could amplify such jiggling. The electrons and wires jiggle too, everything's jiggling.
Good noise generators.
And that's, yes, that's right. And so they make electrical voltages which fluctuating. So if you have a good amplifier, you can get a rushing noise all the time, and it's easy to measure, and so on. As a matter of fact, the first determinations of the sizes of atoms was made by measuring how much of the jiggling there was, because you can imagine, you can see that how much this thing wiggles depends upon how big the molecules are and so on, and how many there are. So, of course, in the beginning, when there was a theory of atoms, there was a lot of evidence for it, but there was no way of measuring or estimating how big they were at first. The first estimate was made, I think, by the intensity of the blue of the sky, which is curious, but the more accurate one is the one on the jiggling. Einstein made a lot of the mathematics for the theory of Brownian motion, this jiggling, and these equations were used to compare to experiment to determine the sizes of atoms. Since then, there are much better ways of measuring the sizes of atoms. What else can we say about the jiggling? Do you have any other points? Yes?
I mean, I don't want to get too technical.
You can now, because we've got all the untechnical people.
When I was a student, it
Yes.
was an experiment I was to set up for the dualismus of wave and particle. I wonder how that is today. It's a two-slit part.
Yes.
You know, if you have one slit.
Yes, I know. I want to discuss the two-slit experiment in detail later on, a few days from now.
Because
in
I
all
was actually
detail.
setting up the counters.
Okay.
You know, and I was.
Yeah, well, we're going to describe that very experiment, and therefore, if you don't mind, every one of your questions, I always seem to put off. But let's say it this way. They're very relevant to what we're talking about, and I had planned to talk about them. I'm not going to leave you off at the end. I'm not cheating you. Yes?
Okay, so my question yesterday was in
Yes.
regard to it's not clear to me why
Yes.
Feynman diagrams should actually manifest when we look for them.
Why
Because,
does-
because you know, the actual exact solution is an infinite sum that we can't do of all
Right,
the terms.
right, right.
In theory, so why in nature do we find the terms?
Because we're finding the answer to something. Let me show you something, okay? Suppose that the right answer to a mathematical problem is 1 divided by 1 minus 1/100th. And suppose I don't know how to divide, because it's very difficult. This is imaginary. This is analogy. The analogy is that I have very complicated equations I can't solve directly. But there are certain other operations that I know how to do more or less easily. So, yes, now we could say that this would be equal to 1 plus 0.01 plus 0.01 times 0.01 plus 0.01 times 0.01 times 0.01, which we write as the 3 times, that's the cube, and so on. Now the fact that, and so on, forever, it's never correct if I stop anywhere. But if I keep on going, let's say it goes 0.1 times 0.1 times 0.1 times 0.1 4 times, or you know what this cube means, I presume. 4 times, and then it goes 5 times, and so forth, okay? Now, if I wanted to see whether my theory agreed with experiment, so I measured something that the theory says is this big, all right? But I can't really calculate that because I don't know how to divide. You understand it's an analogy. Of course I know how to divide. But I do know how to multiply and add. And so I would measure this. Let's say I'd measure this and I'd find out the result was 10103 or something, whatever. I want to know if it agrees with experiment. I mean the theory. Let's say it went to here. That many places. That's not a decimal point. That means I got it that accurate. Okay, I got it accurate. Yeah, right. And these are significant. I measure it again and again, and it always agrees with that. And now we want to find out if it's correct. Then we could do it this way. We'd say, well, if it was a sloppy measurement, the answer's 1. That means I drop all this stuff. But I could do better by adding another piece, which is the first piece. But the next piece turns out, if you multiply it out, to be double 1. And the next one, if you worked it out, no, 0.1 times 0.1. 4 zeros, 6 zeros, it's 5 zeros and a 1, and so on. Now maybe, to make the analogy better, it gets harder and harder to calculate it's hard for me to multiply. It takes a lot of work. Here I have to do more multiplying and more multiplying, okay? So I can only do a few of these terms. Nevertheless, you see, if I do a few of them, I get an excellent approximation to the answer. So you say, why is it valid? It's valid for the following, to leave out some terms, when really the correct answer is a sum of all the terms. The answer is that the higher terms are contributing less and less. We hope, anyway. We can't calculate them exactly. We're not going to compute them exactly. We're going to stop somewhere. But by a mathematical argument or by guessing or by noticing how each one is going down so well, we suppose that the higher ones are smaller and smaller. So if we forget only the first 4, say, then we would get an answer that was presumably rather accurate. We could estimate that the next one is 100th time smaller than that, perhaps. Of course, all these estimatings and so on are unnecessary. We actually can carry it out in this example, but it's by analogy. We imagine it's hard to do all the arithmetic. Then we would say the answer is 101001 and could conclude, for example, 001, let's say, and could conclude from this example that it disagrees with experiment. Or if it agrees, it depends on what the experimental result is. It could agree. It could agree. The point is, we don't have to calculate mathematical quantity exactly. If the theory is complicated, we have other mathematical rearrangements which are equivalent. That's all it is. And the perturbation theory, so-called, with the diagrams, is simply a way of calculating the successive terms of a series like that.
That's clear to me. I'm not clear why the specific terms manifest.
Because we started with something that we know here, a formula that produces these terms. That's what the theory is.
The way I'm hearing the question is,
Oh.
each one of those terms
Yes.
is a Feynman diagram, and he's asking why should the individual terms manifest as physical processes,
They don't.
each individual term.
All the terms are there.
Like a particular, one of those terms might be a particular kind of scattering.
No. A particular kind of scattering is the sum of all the terms. All the things are happening when there's a scattering. We have broken it up into elementary subplots to analyze it. Each diagram represents a a piece of an analysis. You could say in this case, if you wanted to, you could say, this is called a Schlankus. Okay, now the theory is complicated. It says any number of Schlankuses can occur. I can analyze it by saying either there are no Schlankuses, the contribution from the no Schlankus effect is 1. The contribution from the 1 Schlankus effect is 0.01, and 2 Schlankuses is 0.001, and so on. But in any real situation, there's an arbitrary number of Schlankuses, and they're in the formula here.
Well, if we look at the decay of a neutron,
Yes.
decay into proton, electron, neutrino.
Yes.
Simple, but there are higher terms.
That's right. That means that the formula for the decay of a neutron is a complicated expression, which is being expressed as a sequence of approximations.
I understand that the first order term
Yes,
is a Feynman diagram, and the second order is a second order term is another more complicated Feynman
that's
diagram.
right. It represents a more
Right,
complicated
and we look in nature and we find the first order term.
plus the second order term,
Plus
plus
second order, whatever it is.
we play them all.
Okay.
We find them all as nearly as we can measure. If we only measured a certain number of figures, then I can't be sure that these are here. But they were invented because this is what we were trying to express. We know this side and we represent it this way. And we just say there are these terms, and these terms are left out because they're so small. I don't know what the problem is.
Yeah, I know.
Well, maybe we can talk together sometime and get it clearer. Have everybody back or no? I see there's still somebody working.
No, yeah, we're all back. He's just getting some.
Oh, okay. So you're all back. You mean you've all been educated? Everything okay? Oh, great. Well, that was easier. He said it would take a half an hour. But apparently you were closer to understanding it than he thought, or he was cleverer at explaining it, or else he gave up in despair.
There's maybe an even higher order term.
Right. Okay. Well, now that we all are together on it and see that there's something deeply puzzling about it, I review the phenomena for just a moment and say a few words about it and tell you things. The idea was we discovered this, that we can get 2 boxes, each of which has 3 buttons on it. There's 3 buttons, which we say 1 or 2 or 3, and we can push a button, and it lights a light, which is either red or green. Do you mind I change the color from red and black? The black light is a little annoying analogy. It doesn't light, it's no good. So here's the measuring light that comes out. You push, yes, you could do it many ways. You push this and the light's red or green. This is button 1, or button 2, button 3. Likewise on this box. And just to review, once finally more goes like this. The boxes are set up and I give you charges for them, or I give you the boxes. It doesn't make any difference. I have, once they were together, they can be taken anywhere. Now, it goes like this. If you push any button here, the light will light up either red or green, and it's about 50-50. If you push a button here, and then push a different button on the box, then the light agrees with the other one only a quarter of the time. That is, if this one gives red, and then you push the other one, this will only give red a quarter of the time. Or it gives black, the opposite color, 3/4 of the time. We've said it both ways, right? And that's very curious. If there were, well, we've explained the curiosity of it for too many times. Now the situation is here that this box has the same prop, that this box will always agree with this one. If you push a button on both of them, then the buttons will give the same color lights. This doesn't have a light yet, so therefore it won't work yet. All right, I'll put the light on it. Good. Now, if you push button 2 on both boxes, then the lights are both red or both green. They always agree with each other, no problem. And, but what's odd is that if you push a button 1 here and get red, and push button 2 here, it'll be black 3/4 of the time. And after a lot of thought and much study, we've discovered that that's very strange. Okay? We can get 2/3 of the time without any trouble, but not 3/4 of the time. So I would now like to say what the uncertainty principle is. I said it once before. I'll just say it again to make it clear to everybody who now understands it, what Bell's theorem is and what the Einstein-Podolsky-Rosen paradox was supposed to be. Okay? And a little bit of the history of it. First, forget the second box first, and think about this first one. If when I push this button I get red and green, then if I push this one and it agrees or disagrees, let's say 3/4 of the time, that's impossible unless, if we imagine there were cards under there or something like that that were set, that when we started out that this was going to be red if we pushed it, and if we pushed this one, let's say it was going to be green and this one green, then sometimes when we pushed a pair of buttons like this pair, we'd get them to match. And that would be 1/3 of the time because we could pick the buttons in every pair combination. And there are 3 out of all of the 6 different ways of choosing, 3 different ways of choosing pairs, one of them match. That one would give a match, that would give a not match, and that would give a not match. So if I pick 2 buttons at random, I'd expect they'd match 1/3 of the time, but actually they only match 1/4 of the time. The easy example would be if they didn't match at all. Then you would have to say, sir, in either case, that something happens, that when you push this button, if they were red, green, green was a set that they would have made if I had pushed them, then when I push this one, I must change it somehow because the experimental result is 1/4 of the time. So when I push this, the only way to explain that is to have a machine that if I push one button, it changes the ones underneath. Now, if we go to nature and look at it and say, well, what happens if I looked at all the buttons at the same time, that I pushed this and got the result and pushed that and found all the results will always repeat. For example, nothing would ever change, then I'd be in a pickle. So, but it is true that we're only allowed to push one button at a time, and furthermore, it does turn out that when we push a button, let's say this one and gets red, then this one is green, say, and we push this one again, it's no longer red. So we have experimentally noticed that it is true. It's quite possible and perfectly true that we could imagine it this way, that when we push the buttons, they change the colors of the other lights. I remind you, if you push the same button again and again, it always checks out the same color. I start out and make sure this is red by pushing it 8 times. Then I push this one, it's green, it'll stay green all the time, say. Then if I push this, it's possible that it be green now. Okay? Otherwise, I'd never be able to explain this 1/3. Yes, yes. If you push the same button, it never changes the result if you push it again. You push the same button again.
If you wait a while, it'll still be fixed.
Yeah, yes, in a particular circumstance. Obviously, this is set up for a particular measurement. Yes, it can be made so that it doesn't, in general, doesn't change, and you can push it as much as you want. There are situations where things change, but there are situations where they don't. Yes, you can push it as many times as you want in succession, and nothing about that button changes. We don't know what's happening in the other ones because we can't see. And when you push another one, then you see it's changed. So you could still imagine that there was sort of potential or cards underneath there or some kind of thing that determines what color is going to be. But now we have a new rule that when we push it, it changes what's under the other buttons. And furthermore, we can't assume that it doesn't change, because if we assume it doesn't change, we're going to get in trouble with the 1/4 results, or the 3/4. So therefore, we would have to say that if this theory, well, experimentally it's right, the theory is right, but when the early days when it was first discovered, all the experiments weren't done yet. But when the theory came out that would predict results like this, it was obvious that it was necessary for such results, that if there were such a thing as the potential lights that were going to light, I mean the potential cards under there, that by pushing buttons you're changing the results that you would get for the other buttons. And experimentally it does turn out, just like we said, it's all right, everything's okay. If you push this and get red, then you push this and get green, it is possible when you push that to find it's changed. In fact, it's necessary that you find it changed, because if we keep on thinking about this, we would get 2/3 otherwise. And we don't, for 2/3 of the time, there would be different They would change, and 1/3 they would be the same. But it's rather 3/4 than 1/4, so we have to have it change, and God, thank God, it does change. But that's a very simple view then. There's nothing wrong with that, but to say that there were these things were under here, but they changed. Now to say there were things under here, that is, ahead of time there's a potentiality to be red or green without looking at it yet. We can talk about such an idea. We're going to call a classical view. That means an old-fashioned view. And what Heisenberg said was that the old-fashioned view, if it's tried to be maintained at all, would have to have in it an additional new feature that it shall be impossible to determine what color this one would be without changing the potential color that the other one would be. In other words, by measuring that, by pushing that button number 2, you've got to change the colors under number 1 or 3 if you wanted to picture it with color. And we see why we have to do that. Otherwise, we would get 1/3 and we wouldn't get the result today of experiment and at that time of theory. Historically, however, Heisenberg's statement wasn't measured with this particular box business, and he didn't have this nicely, which took 40 years of patient thinking to get the simplest possible example. He had a more complicated example, which was measuring something called a position of a particle, which is an idea that anybody classically would think. A little ball or an electron or a particle would have some kind of position, and you could measure what it was. It would be a number. It would tell you how far it is from the east wall. But 3 numbers if you want, plus that wall, plus that wall. But let's talk about motion just this way. There'd be a number which would tell how far a particle was from a wall. There was another thing one could measure in classical physics, which was something like the speed. Actually, it's called the momentum. It's the speed times the mass. It's a thing that tells you how well it coasts. And you could also measure the momentum of something. Obviously, you can measure its speed, and you can measure it as accurately as you want, and the position as accurately as you want. But according to the mathematics that he discovered, Heisenberg discovered, he saw that the implication that you could measure the speed and the position both simultaneously and know them, and that they would check when you measure them again and again, was impossible. It was contrary to what the theory would predict. He claimed then that it would be like this, that if you measure the position very accurately and then tried to measure the speed, or the momentum, I should say more precisely, it's the speed times the mass, then if you measure the position again, it would be different. It would be possible to have something standing still, so if you measure the speed, measure the position again and again, it's always the same. But then, if you measured the momentum, even if it's supposed to come out 0, when you measure the position, it wouldn't be exactly the same. In other words, it's not like classical particles in a normal sense is possible only if you allow that measurements are going to disturb the system. That is, if you measure the position and then try to measure the momentum, then new position is irreversibly jiggled, if you want, by the momentum measurement. And then when you measure position, the momentum that you determined before is now screwed up. So if you measure the momentum again, it's not the same. It's completely analogous to our boxes. We measure, let's say, this and then that. We measure this. By pushing this button, it's always red. We're going to check it's perfect. We got a nice measurement of that. And now we try to measure this. Okay, we measure this and we see whether it's green, and we keep checking it's nice and green. Then we go back and see if this is still red. If it were red before, I forgot to say, let's suppose this were red. This is green. We look back, it might sometimes be green. In other words, it can change. This is a lot easier than positions, because positions can have all kinds of numerical values. Could be here or here or here or here, and here we have only 2 values, red or green. That's why this is kind of fun. It's easier to work with than numbers, which can have all kinds of values, and mathematics is more complicated. But here it's much easier. But you see then that the theory must predict that if you measure something, if you thought classically that there are these things under here that you're measuring, that this, whatever it is, this is the greeniness of this thing when you push 2, whatever it is, then you must allow that when you try to measure 1, you change whatever it is, the greeniness or redness for a 2 measurement. In other words, you can't measure 1 and then measure 2 and expect that it doesn't affect number 1, okay? And that's the general idea of the uncertainty principle, which more generalized says there are pairs of quantities such that if you measure 1, you cannot allow that you try to measure the other one. It doesn't change the first one, okay?
Irreversibly jiggle, is that what you said?
Yeah, that's what I said. I meant that was an informal way of saying it changes the value. You know, right, in a way that can't be undone, that's completely lost, that the information is now lost, or partially lost.
It's like shouting at your way.
You mean it's a reversible change that you...
It's a perturbation that you can't reverse.
It's true. It's true. Anyone who's married knows that all of the arguments that you've ever had through the entire married life come out in one great well on the next argument. Yes.
Momentum has increased immensely.
Right.
That's the historical way that understanding the concept
Yes.
came out, that there is too much of a focus on the jiggle. Because there's a lot of systems at the atomic level where you only get one shot at it. You only get one measurement. What you do is you prepare a situation, and you, for instance, in a beam, you can say, I'm going to have half of them, I'm going to do position measurements, the other half momentum, and I only get one measurement.
That's right.
And the jiggle doesn't make any difference.
I know.
It says I can only, there's limitations on how I can prepare the system.
That's another way of speaking of it. The preparing means that you want to be able, it's a different idea, but it's the same idea. Suppose that I said that I have some way of setting it in. That's preparing it, so I know what their red or green are going to be. The answer is I can't set it in the way I want. This idea that I'm setting them in like this won't work. Even if you allow, I'm only allowed to push one button, I'm going to get in trouble in saying that I can set in particular numbers underneath. It's the same. You see, you're talking about predicting and preparing, but preparing is always done by, can be thought of as by measuring something else to get it right. It's another way of preparing. I could make sure that this is a red by pushing this button, checking that it's a red. If it's a green, I throw it out. I try it again until I get a red. Now I know I prepared it, so this is red. Now when I measure this, I change the preparation is screwed up. That's what preparation means.
Is this applicable only to single events, single particles, or is it applicable to massive numbers at once?
It's applicable to any system at all. The system may contain only one particle, it contain 3 particles or 25 particles.
How about a billion particles?
It's perfectly all right. Numbers are no problem. Yes, it could be any number of particles.
Where you have beam collisions. You've got billions of particles.
This particular set of numbers with the 3/4 and the 1 was with one particle, and in this case with 2, and I have 2 boxes. And we're studying what happens with 2. The difficulties, the character of this thing is in the particle. And if you have a billion particles, each one or them are all doing the same kind of terrible thing, all right? So it's a universal difficulty. You're still disturbed. One of these guys that knows too much.
I'm not going to use the term go, I'm going to use your boxes.
Okay.
I could generate a situation in which I have boxes that are making themselves available for measurement.
Right, these. Let's forget the other box for a moment. These.
Yeah.
They keep
yeah.
coming out. Right.
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 Now I can create a situation
Right.
that certain combinations of that box have less probability of coming out.
What do you mean by certain combinations?
Those boxes in which
They're only the
okay,
red
I
ones.
can make it so that only a third of the time you'll get red out of door number 1, and
Why don't-
2/3 of the time.
Why don't we make it easy?
Green.
We always get red out of hole number 1. Does that satisfy?
No, the easy case is the trivial one. I'm trying to make the non-trivial.
What
case.
one?
And that is where I can put a bias on what the measurements are going
Yes.
to result.
Right.
Without ever having made a measurement.
Well, that may be whatever you say, whether you've made a measurement or not, but there is another way of putting a bias, is there? By just by checking what's in the box, and if it's right, sending it out. That's equivalent. It's equivalent because the forces which are making the separations are equivalent to...
But the point I'm trying to make is you don't have to do that.
Okay, yeah.
And if you don't do that, then you
But
cannot.
what do you do, you see? And it's a little, we get into some complications as to how we do that with these boxes.
Certain kind of polarizing filters or filters over.
All right, yes, you can load the boxes with some particular prejudice, yes. But it's very much equivalent. Your filters are equivalent to my taking boxes and checking something about the, just a minute, checking something about the, I didn't say push a button, checking something about the boxes and letting them through if they were okay.
But that process is not one in which a measurement is made.
Whatever.
And that's the point I'm raising.
No,
is
it's
that-
not, it's the equivalent, it's equivalent. A measurement could have been made without any further
But
disturbance.
it's only when a measurement actually is made that you can attribute what happens to the fact that there was a jiggle took place. You're talking about the uncertainty relationship being due to the jiggle.
I've already got all of the difficulties with the other box. I don't need to take this other example. It doesn't add anything, okay? It doesn't add anything. So, a way of speaking would be to say, one of the things is either, I see what you want to say. I know what you're trying to say, which will make more clear when I take the case of two boxes. Let me just get to it in my own way, and then we'll come back. The original, one way of thinking about the uncertainty principle, which I made, which is less subtle than the regular way of describing it, was to say that if we tried to imagine that there was such a thing as the red, green, green, if we pushed a button on one of these things to determine it, it has to change the other one. And it's like that. If we imagine that a particle had a position and a momentum, then if we measure one, we have to disturb the other. Okay? In certain circumstances by luck, but not with position and momentum. No, if you measure position, you can have to disturb the momentum information.
But statistically, you disturb.
That's what I'm talking about. So any prediction that you had made previously is not necessarily right. So your information is lost.
I think it would help the discussion if you tell how you measure position and how you measure momentum.
I don't have to, because I have an example where I'm measuring something else with buttons. I say you push the button and see whether the light's red or green. That's.
I'm talking about the electron.
I know, but I'm talking historically. The situation is I've tried to simplify this thing. If I went through the whole thing historically, we would go all through all the confusions and all of the difficulties that people have had for all these years to try to understand this clearly. So what I've tried to do is take a simpler example. And if I go back now and take all the confusing examples and go and explain all of those, I've made it much more complicated than it need be. What I'm telling you only about the history so you can find out what fits into what you just learned, what words belong to what. And what I'm trying to say is that the uncertainty principle is the statement that if you thought that you knew that you could say what was under here, that if you pushed a button, it's necessary that if you push another button, it changes that button. In other words, what's under here becomes uncertain, or is changed by in an uncertain way, because it's probabilistic, by pushing this other button. That's the idea. That's an example of the uncertainty principle. The uncertainty principle applied to this example, which we've been using as our primary example of the behavior of quantum mechanics. But the original statement of the uncertainty principle was more general and wasn't on this particular thing, and one of the examples was position and momentum measurements. We could go through the standard way of describing Heisenberg's uncertainty principle, but I think that we would only go much slower than if we went this way. Yes?
I just want to get clear on this. If you push the first button, you get red. You push the second button, you get green.
Right.
And then if you push the first button, you could get either red or green.
That's correct.
That would be the uncertainty principle.
That's right, it is.
If you,
Not only do you get it either red or green,
yeah.
but you get it red or green with if this were, let's say this was red, then this was green. You push this button, it's different than this button 3/4 of the time, the same 1/4 of the time. And that is always the same numbers, no matter what there was here before. You understand what I mean? The fact that what you've measured here before becomes irrelevant for future predictions after I push this button.
Like the roulette wheel situation. Yeah.
Something like that, yes. If you push this and it's red, or I don't care, green, whatever. Now you push this and it's green. Either way, the chance of this one being red or green is still, if this were green, 1/4 red, 3/4 green. Sorry. 1/4 green, 3/4 red. The fact it's 3/4 red, prejudice toward red, is not because it was red before, but because this one was green. For instance, if this were red and this accidentally were red when you pushed it, then this time, this is more likely to be green 3-to-1, 3 out of 4, than red 1 out of 4. Okay? But the proportions for this are completely independent of what your previous measurement was. So in this particular case, it's an example that measuring this means that any information you had about the other one before is completely irrelevant in future predictions. Okay? That's the nature of the...
I kept hearing you say when you push the second one, the first one would be the opposite.
No, I didn't mean to imply that. I meant only that it was opposite 3/4 of the time. In other words, it behaved exactly the same way, whether or not, what I really mean, and I made now clear, and thank you for your question, is that pressing the second one loses the information, any information that you had about pushing the first one. However, pushing the first one doesn't lose information if you want to measure the first one again directly without pushing any other one. Because if I measure it again, it always agrees, so I've got the information. So you say, nice, write it down. Now you push another one, I don't need to worry about what I had before. All future predictions of this one are independent of what I had before, okay?
So memory is outside the system.
In this particular system. No, not outside the system, because if I push button 1, I have a memory. I can find out what it is again by pushing it again.
That's the only.
No, it isn't, because if I push button 2 and I knew that was red, then button 2 is got to be green 3 out of 4 times on the average.
But it doesn't know that.
But it happens.
You know.
No, I try it and it works.
That's what I mean.
Well, who knows what? I mean, the point is, no, it's a question of memory. That is to say, the system is behaving in a way that depended on what happened in the past. If this was red, and then I push this one, it's likely to be green 3 out of 4 times, and is different than if this were green, so that it has a remembrance of what this was, if you want.
Memory is crazy.
What's true is that it doesn't remember 3 steps back. If you push a different button, it destroys the information from before, okay? So pushing 2 destroys the information you had from pushing 1. And that fact that has to happen, that if we had discovered, in other words, suppose that in the early days when this was first measured, you say there are different ways. I don't have to push the button. I can look inside the box by some kind of other trick. I got other methods. I scatter neutrons. I hokey pocus. I do something else to determine what this button would have been if I pushed it. After all, there are switches in there. After all, I can look at the way the thing is loaded before I push the button. That is, I make a different kind of measurement by a different method, which is to give me the same information. Now, if I could describe a different method which would have found out about these, which would not destroy those numbers, I never could get the 1/4 results that we were talking about. It's impossible. Well, Heisenberg's uncertainty principle went on to say, well, that not only does it change the measurement, but that no other way can exist to measure things that will disturb it less. There was a minimum amount of screw-up that you had to make when you measured button 2 about the information of 1. Okay. Now, this kind of a picture was a kind of a classical picture, and Heisenberg was talking about the relation of quantum mechanics to classical mechanics. Really, Heisenberg's principle can be looked at another way. There was old ideas of classical physics. Quantum mechanics is now different. It would be useful for people who are so used to classical physics to tell them when their ideas will fail. And his statement would be, another way of saying it would be, if you try to talk about something, so you simultaneously talk about the position and the momentum, you'll get in trouble. The logic will be wrong. Something will come out wrong. In the same way, in our case, if we start to say that we could say that behind here is a red thing, and behind here is a green, and behind here is a green, and that's what determines the things, and nothing changes, and they're definite, then we're going to get in trouble. The logic that we make after that is going to fail. So that's another way of saying it. So really, it's a statement of protection, a statement, so to speak, of where the new mechanics, that you might get away roughly with the old mechanics for large regions approximately, but you've got to watch out particularly if you're trying to talk about things which involve, in his case, position and momentum at the same time. And in our case, what's going to happen if I push this and what's going to happen if I push that simultaneously without worrying about the fact that when I push one, it sort of changes the other. But this idea that there was something here which is being changed when I push the other button is still not satisfactory. That's what you wanted. Because we discover that we can make 2 boxes. And instead of finding out what's in here by piddling around in here, we remember one way was to push the button, the other way was to look underneath the switches or whatever. But whatever way we did it, it had to be true. Otherwise, we have an inconsistency that if we determine that this would have been red, and check it with the button, yes, it's red, check, yes. Let's take another. Suppose I found another way to look in here and look inside the switches, if there were any, and determine whether this was going to be read. All right? Now, if it's any good, after I've determined it was going to be read, then I can push the button and check whether it's true. Always works. Suppose. Right? But in the same way, I would get in trouble if after I determined that then I would get in some trouble with the chances. We know that. We know if we can determine this without changing these, we're going to get in trouble because we're not going to get the 3/4. But there is a nice way, so you could always say now with Heisenberg that any attempt to measure this by any method at all is going to affect it. And that's perfectly happy and satisfactory if you would say, well, that's very easy. I'll just imagine any piddling that you're doing there inadvertently turns something in there. But there is a way, a magic way of determining what's here without touching this one. Just a different way, which is to measure this other box, which has been correlated with it that we talked about. We have this special circumstance that we can arrange things so that what this one gives can be determined by pushing that one. Now, because this box can be anywhere inside of cylindrical blockhouses or whatever else, it's a bit of a strain to suggest that when you push that, it changes this. And so we have this puzzle that we would like to say that when we determine what's in box number 1, we would have to change things in 2s and 3s if we took this old view that there is a potentiality, that there are cards inside or something like that. So that the idea that there's cards inside or something like that, there's 2 ways of doing it. You can either say there's a marvelous force that exists at any distance instantaneously through blockhouses, through copper walls, through quartz. There's nothing you can do to affect it by doing something in between. Or simply to say that the old ideas are completely wet, that we can't talk logically about there being potentialities for red, green, and green, or for any other potentialities until we push the buttons. That to say what they might have been before we push them is no longer going to be permitted. We can't start to think, well, let's see. In the beginning, it could have been that when I pushed whatever I set it in, when I set this in, I could say something like this. This is where all our trouble comes from. We say, let me see, I haven't pushed them yet, but there's various possibilities that when I push that, it would be red, that one green, and that one green, or that this one would be red, 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 or whatever. But these potentialities, physicists do not permit themselves to talk about anymore. They just say, after we push it, what it was, and don't try to talk about what it might have been if we had pushed it, if we haven't pushed it. In other words, the only things that can be described are things that have already been measured and not things that are potential.
There's always chicken in the icebox.
Perhaps there is. But you can't tell until you open the door. And opening the door may make the chicken disappear, or maybe not, with certain probabilities. But there's always chicken in the icebox. Now, whether that's true or not, we can't say that. In other words, even if we made up a theory that there was chicken in the icebox, we'd open a door. We get into difficulty because we can find another icebox by which you can determine whether the chicken's in there by opening its door. That's this one. And so you're really right about this chicken in the icebox door business. And so when the door's closed, we can't say whether there's chicken or not in the icebox. We try to say, I don't mean we can't say there's chicken or there's not chicken because we don't know. I mean the whole idea of saying it's either got chicken in it or it hasn't got chicken in it produces a failure.
And the other one
It says
is
irreversibly jiggled?
No, you can't use that anymore. You can't say that it is either one way or the other, and when you open the icebox it changes, because we can find out what was in the icebox by another measurement, and that gets inconsistent. Yes. So
The old game of trying to figure out if the light is on when the door is closed on.
it's gotten worse. You see, because with the old thing, the question is whether the light is on or the light is off when the door is closed. It seems legitimate to say the following. Either the light is on or it's off. There are 2 possibilities. Now let me start thinking, okay? The beginning step is no longer allowed. Before we push the button, we can't say, if we do, we're going to get into logical troubles and not be able to understand how nature works. So we have to train ourselves, and that's what physicists have done. They train themselves in a negative fashion to be very careful, not to say things like, well, let's see. This is either red, green, green, what would happen if I push the buttons, or else it's green, green, red, or else and so forth. Those are possibilities. Now I'll push the button to see what I get. The whole statement that these are the list of possibilities is no longer permitted. So you have to be very careful with the logic, okay? And what I'm going to show you in the next days is what kind of machinery we actually do use and what kind of thinking we actually do use in order to predict results like this, because we can predict them, you see. We do have a theory for all this. It's not that chaotic, but it's not at all like what you're used to. Simple ideas of logic, the simplest idea that these are the possibilities, and let's see which one it is not permitted. You get into trouble. What is permitted and how you can do it so you don't get into trouble will be described in future workshop sessions. Okay. Now, but now I'm trying to explain to you why I claimed in my workshop advertisement that I would tell you about the uncertainty principle and Bell's theorem and Einstein-Podolsky paradox, because I have just done so. It's all finished. But you will not be satisfied because you don't know where each of the pieces are. So first I told you where the uncertainty principle was, the statement that by measuring something you've got to disturb the predicted expectation for something else. But it's more subtle. You're not allowed to have an expected predict for something else anymore and say it's changed. You have to have it be more abstract in order to be able to understand this situation. There, of course, is another way, and people have proposed it, and that is to say that when you push this, there's a marvelous influence that spreads instantaneously through all the world and changes those other things which were correlated that you expect to measure, okay? This is possible, and that's a model that you might prefer over the idea of saying that there's no such, you can't talk about the possibilities before you make the measurements. That has turned out, people have tried to do that. There are two directions in which you can go. You can say, yeah, there's always this instantaneous action and it does exactly the right thing and it doesn't depend on the distance. But that's an unnecessary complication, so to speak. I mean, it doesn't help any. It's perfectly okay, but since an action can go at any distance without any effect, there's no laws about it except that it does just exactly what you want. So just describe what you want and never mind saying that it's done by some special law or some special magic, because that special high-speed interaction is only to protect your prejudices about the way you'd like to think about things. That's all it was for. It didn't change any results of what you'd expect for any experiment, which is what physics is about. And so, don't bother to say it. It doesn't make any difference. If you want, you say, this is so puzzling, I'd like to say there's an instantaneous action that goes at infinite speed everywhere and is not affected by anything, only to make the answers come out right, okay? Is okay. Well, you want to, okay, but it doesn't make any difference, right? Because the answers come out the same. So, yeah, so we just don't bother with saying it, most physicists. Now, however, there's another possibility, and that is that there really is such an action, but it isn't, as I said, that for short distances it's independent of distance, but for long distances it disappears, that it takes a little bit of time, that it does something. Then the predictions will be changed. For instance, if these boxes are pulled further apart, then this will not agree with that anymore. Or if I measure this too quickly or not quickly enough, early enough, I can't predict what that one's going to be, and so on, because there's the delays and there's character to the interaction. As soon as the interaction has character, other than this universal marvel that goes at all distances, at all speeds, instantaneously just to get the right answer, but it is more complicated. You say it takes time to go, or it weakens with distance, or anything like that. It makes new predictions. So, some people, early on, not many, but some, proposed just that. They couldn't take it. And so you said there must be an interaction. And they can't take it that the interaction is so fast and what they call non-local. It doesn't propagate. It really doesn't take time to go anywhere. It doesn't go through anything. There's nothing you can affect it with. So it must be affected by something, and made various predictions of what it might be affected by, and then would propose experiments that you would have to do to check out whether or not this magic force was doing the slightly different thing they wanted it to do than to be perfect, okay? And these experiments that have been proposed never work so far. Now you say, oh, well, I can certainly invent one which works over the entire range that's so far been checked, if I'll tell you what it is, right? You can just make the rules so that it'll go further on, that it'll happen only 1 light year apart. You've got to move these a light year apart or you'll never see any effect. Okay, we can't do that experiment. It's still possible. You could have it if you wanted, but there's no evidence for it. And all attempts of this kind to make those suggestions, which were not stupid, because this is so peculiar, it might have been that the prejudice about the way the world worked that you had previously was in fact right, and that there was some delay in the interaction. It's a good suggestion, only it isn't so far true. So what we do in physics is we take what we find so far and try to extrapolate it to see over a wide range of experience to see if it works. It's always possible that the theories be wrong, that there really is an interaction, that this really doesn't work, what I told you with the 2 boxes when they're a light year apart, or some other distance. It's always possible. We're not trying to find out for certainty what the world is like, but just what we've seen so far. And we can summarize everything that we've seen so far by saying that this interaction is instantaneous and magical and does exactly what we want to get the answer over here, okay? And so we just don't worry about it yet, because we have seen no effects on various things. People, however, are aware of the possibilities and are making suggestions for experiments, but so far all of those experiments have failed. My personal opinion is that they're all going to fail, that the logic is wrong, that there was the prejudice that you had, a rather deep one, of course, about the potentialities for what's going to happen before you push, that must mean something, that the chicken in or out of the icebox has got to mean something. There's the only 2 possibilities, but that logic is wrong. I think that's really the way the world is, that our ideas that came from experience in the large-scale world are that wrong. That's all it is, but that's an opinion held by most physicists and perhaps incorrect, but we'll find out someday if the thing doesn't work. So far it works. So let's talk about so far, okay?
Would there be a way of changing logical?
I'll show you how we have to think logically, yes. Yes. We have to just be careful not to make some statement like, see, it isn't the fundamental logic, like you say, I'm going to assume a variable x can have 2 values. That's not what we're saying. We're saying there is a piece of chicken in an icebox or else it isn't. But we're not going to start to talk about what's in unless we open the door. Such ideas may not mean anything. It may not be an inside to the icebox, much less whether it's lit or not. As soon as you close the door, there's no inside, or whatever. So it's not logic, it's a question of what you're going to allow yourself to talk about.
So you're being rigorously operational.
Yes, it has to be more operational.
There's the other point that the uncertainty principle makes causality irrelevant. Because since you can't determine the present...
No, you can. If you measure whether this is a red light or not, it's perfectly all right. It's just that attempting to measure another thing about the present simultaneously changes what you found before.
Yeah, but you have to know where you are and where you're going in order to determine whether...
Yes. To determine exactly. But you remember I said that there would be probabilities, that we're not able to predict the future exactly. We only predict the probability of different events. And if you want to say that, you see, we're not in a situation where we know this present and that determines exactly the future, because it's not the way it appears to be. We can set up the present as perfectly as we want, and the future becomes uncertain. It's only probabilistic. So it's consistent with the thing. Now, just to continue with this identification of words, all right? It was Einstein, after Heisenberg talked about the uncertainty principle of position and momentum measurements, most physicists understood it and everything okay, and took this point of view. But Einstein and Podolsky and Rosen didn't like it particularly, and they wrote a paper saying they didn't like it. And that's what it amounts to. What they didn't like, they took the analog of this experiment, except for position and momentum measurements. They pointed out it was possible to get 2 particles separated. So by measuring the momentum of one of them, you would know ahead of time by the correlations that would determine the momentum of the other. Just like if we push this button here, it would be just equivalent to pushing that button there, because they always agree. So you could make a pair of objects so that the momentum of this would always agree with the momentum of that. Actually, the momentum were opposite directions, but that's technical. You could put it through a mirror. So you could make it so the momentum of this would always be the same as the momentum of that, and the position of this would always be the same as the position of that. So you measure the momentum of this one, and the position of that one. And that was against the uncertainty principle, they said, because by measuring the position of this one, surely you can't be changing the thing over there. And Heisenberg would have said in the older way of speaking, if I would be crude, that by measuring the momentum, you jiggle and make unpredictable the position because of some mechanical effect. We have to deny that now. We can't just say it's a mechanical effect, as we've now noticed, that we can't say, it's easy to understand if you push this, you might have some wheels turning to change that. But if you push this, you have wheels turning over here to change that? No. So they just pointed out this little difficulty that you can't take the classical point of view that a particle has a position, well, that if you measure the position, that there is a position of momentum, when you measure the momentum, you change the position. That's too crude, because you could measure the momentum of this other one, and it won't change the position of that one. It's just, this is a completely analogous. It's an example of an Einstein-Podolsky-Rosen setup. The idea is that by measuring over here, where it's practically inconceivable that this could be affecting that, you can determine what this would have been if you didn't push it. But we don't like to talk about what it would have been if we don't push it anymore. That's the way we escape from that. And it was already known by the time Einstein and Podolsky wrote that was what people were saying. But they were objecting to that, and they said that that's not an adequate description of reality. Or perhaps it's not an adequate description of reality, but it's an adequate description of whatever we're able to predict. And people who've tried to increase the reality of this by making this a real wave or something like that have always produced predictions which don't agree with experiment. So that's where it stands. And that's, now we've talked about the uncertainty principle, and Einstein, Podolsky, and Rosen. All they said was there was such a situation, which we've already used. Did you have a question? Yes.
I've always been impressed by the fact that I've not seen very many comments on the philosophical premises laid down by EPR, which is, if I can predict something with complete certainty, there's an element of reality that I can attribute.
Yeah.
And basically what you're saying is that's the piece of the action that you have to let go of.
That's
to
right.
create the dilemma.
That's right. You've got that. Yeah, just because I can measure, yes, right.
Classical reality
Finally-
is fixed and this reality is not.
It's a different kind of reality. The world has to look different. Yes.
Is that partially what you were saying too, that it's not a matter of the logic yet, that we haven't gotten to the new logic, but that right now we have to let go of the assumptions or other ways?
Yes, there are two ways always of doing it when something doesn't work. You can either say that you're not allowed to make certain steps of logic or to make certain perfectly obvious assumptions that look perfectly reasonable. Both of them are difficult because we don't like either of them. The logic looks good. There's two ways of doing it. The easiest way, and the way that we've all chosen for practice, is to say you can do as much logic as you want, but you've got to be very careful about the kind of assumptions that you make about what's real and what's there, especially about potentialities. The whole thing is summarized this way. You can't say that this thing has the potential for producing red, green, and green. That's there before you push to check it. Okay? Wheeler has said, in a way, it's one of these beautiful aphorisms that are shorthand, which you can only understand after you've finally understood the whole. Oh, you want me to wait a minute for your tape? Okay? Wheeler has made one of those lovely aphorisms to describe this, which you'll only really understand thoroughly when you understand the whole thing. But it helps to remember. He says, there's no phenomenon. A phenomenon is not a phenomenon until it's an observed phenomenon. In other words, you can't tell what's happening in there, or there's no chicken, or there isn't chicken, until you look to see. So you only talk about what you can look to see. Wheeler, John Wheeler. Oh.
We're away from probability, we see it returns.
I don't know.
Is that really?
Maybe, I don't know. And then finally, in the list of things that are in the prospectus for this workshop, there was Bell's theorem. Huh?
Taking care of all that business.
Yeah, I want to take care of the business. I advertise something, and I have to show you that I've already done it. The other one is Bell's theorem. I've already told you about that, I think, and that says is simply a mathematical statement of the fact that situations like this can arise, where the actual probabilities observed are impossible to explain by a classical type of card-filling boxes scheme. If the odds had been 2/3 that we would get a different color and not 3/4, we could have explained it easily. With all this logic would be okay. But that in quantum mechanics, some of the probabilities that would be predicted by quantum mechanics would disagree with the simple arguments in a situation like that, like this, that you get by thinking about cards being in the boxes. In other words, quantum mechanics would produce effects like this. The mathematical theorem is more complete. It tells you how much the effects are and where to look for them. But we have an example of such an effect, and that's all we need to show that something, that quantum mechanics is odd. You don't also need a theorem to tell you how odd it's going to be in every case, which is what the theorem was. Okay? The theorem was in fact inspired by such discussions of this for special examples. And not quite as simple as this one, where we have only 3 measurements, but measuring spins of electrons that were correlated and so on, where you can measure something that has light, or the polarization of light, where you can measure a whole lot of different possible places. It's if we had boxes with lots and lots of buttons. The point would be that some of the odds on the buttons were against the common sense, old-fashioned common sense. Yes?
I was just going to point out that actually Bell's description is very much like this description in the sense that in his setup, you actually do have to look at 3 different polarizer settings in order to get the inequality, just as you have to have the 3 buttons.
You need at least 3 before you get into trouble. You can show that there's no situation where you can measure just 2 things where the probabilities are not something that you could imitate with cards. So that's why it involves 3 in his theory. Yes. We're there because, yes, where the thing is done general, or you have a special example, there must always be a parallel between a general theorem and a special example of a kind. In fact, I personally find different people are different. Some people think abstractly right away very well. I don't. I always have to have examples to understand something the first time I hear it, and then I kind of generalize from the examples. Other people like the general thing and then try to use it on examples. So I like this way of thinking of things, a nice, simple example where all the things are perfectly clear and there's not a lot of mathematical stuff that confuses me. Which if I study hard, I can sort of check out. In fact, what I do is the opposite. I take the mathematical scheme and try to find a case like this. I didn't find this one. I found one with 6 buttons. Okay? I mean, my original one was more complicated than this one of Merman, which is beautiful. Beautifully simple. Mine had 6 buttons. It was almost the same, actually, but it wasn't quite as good.
Can you give us a practical application of Bell's theorem, the way you talk about the sunset and the moon? And
No. No, we've talked about it. There's nothing magical about it. It's just a mathematical statement that there are situations in the world where you make measurements like this which will have this kind of paradoxical probability answers. You know, the answers will be not understandable by supposing it was done with cards that were shifted and stuff like that. Okay? That this kind of a thing can happen. That's all it is. It's a statement that this kind of a thing can happen.
Who added this non-local reality idea?
I don't know about non-local reality. What?
2 sets.
Huh?
Who? You mean the 2 sets of different, 2 sets of 3 boxes?
Right.
Well, Einstein, Podolsky, and Rosen are the ones that emphasized this kind of a situation. It was already known to others what would happen in this situation. In fact, they could use the mathematics of the theory that existed for this kind of situation, but they didn't like the result. And they simply said that. They said, can quantum mechanics be a complete description of reality? Because, as you pointed out, they made an assumption about reality, which was that if you could determine what was in that thing, that had to be somehow real. And if you could determine by doing something over here which didn't affect that, it couldn't affect that because there was no independent of distance and simultaneous and so on, then that was somehow real there, and they wanted to make it real. They insisted, in other words, that we'd be able to say that there was some sort of potential cards in here that are determining what happens. And that's just what we don't say. So, yes?
Yesterday you described that if you go through this process of pushing number 1 and it's red, then you push number 2 and it's green.
Yeah.
And you push number 1 again, it could be red.
Right.
But now if you go to the second box,
Right.
it still hasn't changed number 1.
Correct.
Although number 1 here may have been already changed. Would that preclude any forces between them in operating, because
In
obviously...
a kind of way it does, doesn't it? It means that, yes, that's true. That if you were to say in some mechanical way that when you push this, you'd change that, then you would think that if you kept pushing the other ones, it would keep changing that, okay? But it doesn't. Any further actions over here have nothing to do with what happens there. The only thing this is good for is permitting you to know what you would have gotten if you pushed, or rather, better, I should be careful, permitting you to predict what would happen if you pushed the same button, period. That's all it's able to do. After that, the first time, and after that, nothing. That's an interesting point, and I have not analyzed that very carefully, and I don't know what the people who invent these waves have done with that aspect of it, okay? Why it disappears after the first measurement. It's an interesting point that I have not studied. Thank you. I'll have to look that up, into that. So that sort of helps to make it impossible. It makes these waves get more and more complicated. To explain what? A result which we can describe over here and forget about this if we wanted to. It's just that this is correlated with it. Okay? So, I guess that takes care of all of the three things. Okay, now I've sold you what I advertised. And now I would like to, well, we're not finished yet. Okay, we can talk about a few other things. And that's this. Let me ask this question. See, you don't know what can be done and what can't be done, so I'm going to tell you something. Maybe we could make a copy of this box without bothering it. That is, we can make another box over here. 3 boxes. Ooh, what a wonderful idea. 3 boxes. And let's make it so that, is it possible? This also has a 1, 2, and 3. Is it possible to make 3 boxes such that the following happen? That if I wanted to find out what this would do, I remember last time with 2 boxes, I could push that. If this is red, that'll always be red. After or before. Make it 3. Then I could push this one also to determine whether this would be red. For example, if this is red, then this is red and this is red. Can we make it work with 3? In other words, in nature, is it possible to arrange that there are 3 boxes which have the following property? I could look at any box to determine whether this was red by pushing any one of those buttons, not necessarily this one, and they'll always agree. All 3 boxes always agree. Likewise, if I push button 2, all 3 boxes would always agree. Or if I push button 3, they would always agree. Then we were going to get in trouble. Because it takes a little thinking. I haven't thought it out to make it simple. But because we have another box by which we could make another measurement over here, so to speak, without touching it, we're going to find it's impossible. Now, it's not impossible simply because it's logically impossible, but, I mean, it's logic. But if you count the number of cases that you get, that is, you measure this box here, and this box here, and then ask how many times the pairs differ. They have to be a third. You see, this time I would be able to make 3 measurements, and I could list the 3 measurements. I could tell you what was 1, what was 2, and what was 3. Now, maybe it would turn out that one time it would be red, black, black. Those were the results, or green, green, I guess. Those are the results of measuring 3 different boxes. They're all available. Another time it could be green, red, red. The 3 different boxes, or maybe red, red, red. Because I have an experimental situation with 3 boxes, and I push 1 button on one, button number 2 on the second box, button number 3 on the third box. So this is number 1 on box 1, or box A. This is number 2 on box B, and this is number 3 on box C. There's nothing wrong with that. So here's the 3 boxes, A, B, and C. And remember that whatever I get on C would be the same if I pushed it on A, same number. Now if I make this long list of possibilities, which are all measured now, those are numbers that are in notebooks. They're not in boxes anymore. I pushed the buttons and I wrote the answers down. Okay, after I've done this for a week and I've got thousands of these, I go back and I count. Nothing. It has nothing to do with the boxes, nothing. I count how many times do I get out of all this a pair, 1 pair equal, and one. I got to get at least 1 pair equal out of every 3. See, I could think of all the I just have to count. Let me see. What do I count? I count how many times a pair that match appear. And here's one. It depends. How many times? Okay, let's say how many times a pair match appear in the column 1, 2, plus how many times a pair appear in the column 1, 3, or how many times in 2, 3. And I've counted all the pairs. And you see it can't be any less than 1/3 that pairs match. This is the pair that matched. In this case, these didn't. In this case, this pair matched, but the other two didn't. So I must get at least 1/3 matches. I can't get only 1/4 matches because I've written them down. I mean, that's impossible. So it's impossible. Therefore, something would be wrong if I could do it with 3 boxes. And nature doesn't permit us to do it with 3 boxes. It's not possible to arrange in quantum mechanical world, in the real world, in other words, 3 boxes which have this property. And if I push any one button here, I can determine what the others 2 would do. Any button. All right? What is possible, it's curious, what is possible is to arrange 3 boxes such that they all agree with hole number 1, say, for instance, button 1. I can take 3 boxes. In fact, I can take 3,000 boxes. I can make as many boxes as I want. Let's take 3 first because you get nervous. So if I push button 1 and say it's red, it'll turn out that any of the other boxes, if I push 1, it'll also be red. Right? All right? But if I push number 2 on this box and it's green, say, it doesn't mean that it's green here or it's green here. It doesn't agree in general, necessarily, all right? You understand? I can make it so that this box will agree with all the other boxes if I push 1. So I can use any box I want to predict what 1 is going to do on any of the other boxes.
It was the first one.
Number 1 box. I get a special arrangement. I made a special arrangement with the number 1 connection system, yeah, where I make multiples of these boxes, say 3 in this case, or 5 if you want, but which have the wonderful property. Let's make a lot of them, okay? I keep doing this. You can go to 3, 4, 5. I'm jumping too fast, but you can. It's the same idea. And I have a lot of boxes, and it's possible to arrange it by possible to get things set up. It's first position. No, first button. First button and first push. No, any number of pushes. If you just if you don't push.
And it came green, would all the rest of
No.
and 2 C's the first push be green?
No, let me say exactly what happened. You're probably guessing right. Let me just say it then. Yeah, you push 1 here, and it's red, let's say. Then you can predict that if you push 1 here, it'll be red. If you push this one, it'll be red. If you push this one, it'll be red if it's number 1 hole. Okay. However, right, if you push number 2 now, or push 1 here and 2 there, you can't predict what it's going to be, but 3/4 of the time you can guess it'll be different. Okay? Nor can you predict what will happen on this one. They won't agree. In other words, let's say I push this red, I got red, I look in this box, I push this one, it's green, okay? This does no longer have to agree with this. I can push this, it wouldn't help me to know what this is, and pushing that after I pushed 1 doesn't do any good. Nor, in fact, is it true this way, that if I started this out and I know they all agree in 1, by pushing 2, I can find out what I would get on the others. No, I'm not allowed to do that. If I do that, I'd get in trouble, as I told you, because I'd make a list and I would be in trouble. A different kind of trouble, much worse, because it's on a notebook. But there it is. I count them, and it's impossible. Yeah.
You say it's only the left-hand position.
Yeah, for instance, you could make it for the other positions, and you can make other kinds of correlations. But now let's say it's possible to make a perfect correlation, but only for 1 position. Okay? A perfect correlation means that you can determine any other box by pushing 1. You can only do that with 1 position. You can't do it with more than 1. When there were only 2 boxes, we had the wondrous fact that we could do it with all 3 positions, correlated perfectly, but no longer, not when we try to make multiples. In fact, if you made multiples that have this property, that are all built, so you're guaranteed they've been built by the same process all the time, so that number 1s all agree, which I'll call number 1 correlated boxes, okay? If you've arranged to make a large number of number 1 correlated boxes, and you don't push number 1, okay? But you ask yourself, what happens if I push 2? Let's say I push 2 on this box, it's green. And I push it on this and I record it. I push it on this and I record it. And I make a whole record of all the green, all number twos. You know what's going to happen? Not all green, no. Because if they were all green, then they would agree, and I said I can't do that, or I'm going to get into trouble.
3/4.
Yes, sir. 3 of one kind and 1 of the other. And which kind? After you determine for a number of these boxes, let's say you had 1,000 boxes and you used 900 to determine what it was, and it was 3/4 of the time green, then you can guess. If you push this button on the other ones, it's red. And they all agree. They've been loaded. Okay? You can even determine what that is by measuring the others and measuring probability. But only by probabilities. All right? This correlating many copies on the same thing is what's really called measurement. Because when we measure something, we were able to make records and write it down somewhere else, so that if we wanted to get the answer, we can look at the writing. So making a copy is analogous to making a record. I could play around with these boxes and throw them away, and I still find out what this one was by measuring this, any one of the boxes. They'll all agree still, the ones that are still left. So this copying process, in this particular case, a copying process which sustains the correlation in hole number 1, or button number 1, is called measuring what the result of 1 is. And the measurement of 1 precludes a perfect correlation in 2. It insists, if you've made such a thing, that number 2, that's 3/4 of the time green and 1/4 of the time red. It's saying the same thing again. Instead of making the same button measurement on the same box all the time, just making many copies. Yes?
I would suggest don't always use box number 1 as the first button you push, because then there's the possible confusion
Between the box
between
label?
the location of it and the fact that it was the first button you pushed.
Oh, I see. Oh, you mean using 1, 2, and 3, I push button 1, you might be confused with whether it's the first button I pushed. In time, you mean? First in time or first on the box. Well, I'm sorry that I made that error. We could have called the buttons PQR or something. It would have been better. Or the left button. That's a better idea. The central button and the right button. Good. Okay, that's better. Now, if there was any confusion, I'll say whatever I wanted to say again. I've arranged things so that the left button is correlated. If you push it on any of the boxes, the left button will give the same answer as on any other box. Thank you.
No way, because it's still the same problem.
What?
The left has to be correlated, only can you correlate the right position for it?
Instead of say initial, don't you think the
No, what?
initial press?
What's the problem? I don't understand it.
I think I think it's probably been mostly cleared up, but it's looked as if you were always correlating the thing on the left side.
I was.
Or the one with number 1 or whatever.
I was.
As if maybe you can't correlate the one
Oh.
on the right-hand side. It would be better to kind of randomly jump around and say, well, let's say we push it.
No, well, if I randomly jump around, I see. Yes, okay.
And then we've got 2 all correlated this time, and some other time randomly choose number 3.
No, just a moment.
Initial, the initial.
No, just a moment. Let me just say something and see whether there's a misunderstanding in reality or just in words, okay? What's possible is to make copies by a certain process, which I can call, for instance, one of the processes of making copies would be, the hell with it. Don't pay much attention to what's in the other, and all correlations are lost. What's in one box has nothing to do with the other. That's a lousy way of making copies. One of the best ways of making copies with the most amount of correlation is there is a special way, a special kind of interaction that you have to make these copies. It's a process, the printing process, whatever, which makes the copies a special way so that what happens with the left button is correlated perfectly. That I can push any one of these boxes and it'll agree, but only for the left button.
But you can make it so that...
However, there's another process by which I can make another 1,000 sets of boxes, but I have to have the interactions different. I have to know what I'm doing ahead of time. So I make the copies. The process of making the copies is different. And for that one, it's the central button, which is correlated for all the boxes. And the third way of making the copy, the correlations, could make the third one agree. And there are other ways of making things so the correlations aren't perfect and so on, but the more perfect ones are the more interesting ones. Is that what you want? I can do one or the other or another, and I can make, we can discuss other possibilities, but I wanted to clear up this. Does that clear up this difficulty?
Could you say instead of left button, any specific button?
Yes, I could choose any specific button, but I can't choose the button after I've made the correlations. The process for correlating it depends on what button I'm aiming to correlate, okay? I got to know that ahead of time. There's a left correlating measurement scheme.
In other words, you can't take a population where number 1 correlates and mix it with a population where number 2 correlates and then do an experiment to find out which is which.
Well, I don't know. I have to think about that. If I mixed them up and then I tried to check which were in pairs, I might be able to figure out which is which. I don't know. Yes?
Do you mean that you don't mean, like in our problem, it's not the initial button, but a specific location?
Yes, left, right, and center. We've been using that one.
So we can only choose one of those locations, but it's not the initial press that we
No,
like.
no.
Because in our example before, it was the initial press, no matter which position it was.
That's correct. That's right. Yes, 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 yes. I see now what was... Good, good. Now we get the problem. Yes. Yes, last time it was the initial press that was correlated. But if this is correlated on the left, you remember, however, that although it was the initial press that was correlated, it's still true that if you don't push any other button, they're still correlated. You can measure either one again and again and again. They always agree, right? It's just that pressing some other button screws it. All right, now, with this setup, you can push this button on any one, and it'll tell you what it'll get for any other one. And you can push it again and again, and if you want, okay? If you pushed another button over here and found out what that was, you could still find out what this used to be by pushing one of these boxes that hasn't been touched before, or has. Depends on how it's been touched.
So those boxes are all loaded that in one particular position, there's a constant, so to speak.
That's right. In one position left, there's a complete and perfect constant agreement, but not if you change, not if you... Well,
Can you change the correlation in a given box setup to say from number 1 to number 3?
no, you've set it up.
You set up initially with 1.
Yeah.
And now I'm manipulating buttons.
No, yes and no. I'll tell you how you have to do. Okay, he wants to do something. We'll come to a lot of things. We'll have fun discussing this. We'll take a time out. It's nothing. We've already understood everything, but this is just to tell you, attempts to beat the game by making copies doesn't work. And this is what but you can do something with copies. Okay, his idea was, we've got the left ones copied. Can I do something to this box so it gets correlated to the right end? Not by touching just this box. I can by taking a whole bunch of boxes into my room and doing something with them, turn the whole system into the other kind. But I can't do it if I only got a few of the boxes. I have to have all the boxes. You say, yeah, but I'm only interested. Can't you just make these few correlated? No, because I haven't got the other boxes. I can't turn these, I have to have the entire population to turn any of them so they're correlated any other way, okay? I can only disconnect the correlations by touching a few. I touch a few, I can screw them up, of course. In fact, an easy way to screw up the correlation of this is to measure that. We know it changes the odds on that one. But if you say, oh, hell, so I screwed this box up, so I'll throw it away. I still know what number 1 is going. Just use another box to measure it.
Could you at some point say how you actually prepare this?
I probably will. It gets a little technical, and I don't know. I haven't prepared that. I'll have to think of a way of describing it in a simple way, a precise example of such measurements.
Right.
Yeah.
That's what I'm waiting for.
In the EPR,
Well, you might have to wait longer than I think.
thought
Yeah.
experiment, when you talk in terms...
Just 2 of them.
Okay, but we talk in terms of if you measure, if they're identical, even in opposite directions, using mirror image to
Right,
make it
right,
the same
right.
and so forth. What was that assumption based on, that you could in fact produce identical, so that you could measure one aspect of
It
one?
was based on the equations of the quantum mechanics that had been developed at that time. The Schrödinger equations would tell you what would be the result of various kinds of experiments. And they're still the same equations today. And so they would use those equations, and he explained how those equations would produce this effect.
Could you in nature produce
Yes.
two particles.
Yes.
That one where you could measure
Yes.
momentum and one.
Yes.
How do you know? Okay, all right. I have to think about how one knows that they're in fact identical, other than saying they are identical.
Well, we don't know whether the particles don't have to be identical. All there is need is that one measurement predicts the other one. Sorry, complication.
Well, I'm identical in the sense that either.
What I mean by
either
identical, what he's
position or
worried
it's
about.
identical.
Yes, that's okay. Well, that's because the mathematics predicts it, and then you check it and it works. What he meant by the identical, this box doesn't have to look exactly the same as that box. I can make the same thing with a blue box here and a green, bad using those colors, a blue box here and a purple box there, or a square box here and a round triangular box there. The particles don't have to be the same. The objects that I use to load them don't have to be identical, but they have to have three states so that I can make this measurement and charge the boxes, but I can be charged with this correlations that we've been talking about previously or now. So the identity of the boxes is not an essential feature at all. Okay, the identity of the results is what counts in this discussion. So because of this, it means that we can do what we call measuring what this button would give, which consists of making this kind of special left-hand copying system and sending you one of these boxes, or 2 or 4. You want to know the answer to? I'll send you another group of boxes, 3 or 4 boxes if you want. And if you want to know the answer, I'll send you another 3 or 4 because I made thousands of them.
These are microcircuits.
Could they be used underwater?
Yes, anyone can be carried underwater and done anything you want it with it, and it'll work. Of course, you got to be careful. There's no leak or the water gets inside. I mean, it's possible to screw it up, but if you protect it, it's okay. But it doesn't be any distance.
Are you in the business of manufacturing these boxes?
In general, we are. That's called measurement. Because what we do when we measure is just say we have an atom, and we do something with it, and then we're able to publish what the result was for its spin or for something else. In this case, what would happen if we push button 1?
Can I order 10 boxes?
Yes, not this particular.
Can dolphins press your box?
Certainly. Yes.
Their rostrum?
Yes, dolphins can press the box. Computers can be designed with random number generators to decide which one of these buttons is pushed and record all the results and so forth. So it doesn't require mankind to do it. You say, but sooner or later the man has to look at the notebook. True, because otherwise we aren't going to know. You can't be us who know unless we look, right? So therefore man is essential to all observation. Yes, for all observation that he wants to know about. A perfectly understandable philosophical principle with no depth, but great profundity.
I'd like to see you and a dolphin facing up to one another.
Well, that would be fun, yes.
We can arrange it.
They have connections.
Yes,
In this last example,
Yes.
you're telling us now that one of the positions is perfectly correlated.
right.
And the rest of the story is that then in the other positions, you'll get a 3/4, 1/4.
Yes.
kind of
Yeah,
distribution.
they're not correlated. I push one here, I might get green. Another one, however, will not necessarily agree. It might be red. If I made lots of boxes and just measured all of these central buttons, I'll get greens and reds, either 1/4, 3/4, or 3/4, 1/4, or something else. It may be a sloppy connections, but let's say 3/4, 1/4, or 1/4, 3/4. And from which way it is, I can determine what I would have got from one. In other words, if it's 3/4 green and 1/4 red, I can conclude that that means that this was probably correlated, that one's red. See, knowing that these are correlated, suppose we know how we made them, so we know they're correlated. Then we know that all these buttons are going to agree one way or the other, either reds or greens, and I can determine which one it's going to be by checking the second button only and finding out whether it's a predominantly green or predominantly red, 3-1. If it ain't 3-1, I'm screwed. Something went wrong with the experiment. It'll always be 3-1, one way or the other. And when you measure with enough of them until you're convinced it's about 3-1, more for the green than for the red, you know why I say you have to measure a large number, a reasonable number, because accidents can happen. Then, after you've determined it's 3/4 green, you can predict what will happen if you push red, not on the same box that you've used, because you know, when you measure that one, you screw up this one, so it isn't going to help any. This one's then 3/4 the other way. However, a box that you haven't touched yet, you haven't used yet, in order to get the statistics on the central button. If you push the left button on that box, it'll be red. Not on the box that you played with already, because in those boxes that you played with already, they're the universal rule. They're all independent then, you see, that if this is green, the chance of that one being red is again 3/4. Yes. And if this is red, then the chance of that being red is only 1/4.
I thought they were all perfectly correlated.
They are. They are.
So what information does that really give us?
That the only information it gives us is that we know what we would get for any box by looking at any other box for left pushing.
It allows us to separate them without.
Yes, so that you can publish what you observed, you say, about the first box, the early box.
You can sneak your assumption back in.
Yes, yes.
What happens if you have three?
That's right. And what happens in nature, on a large scale, if there's anything, it's always this kind of correlations, that at least that are interesting, unless it's just chaotic. So all of the physical world which we analyzed before, where we found laws and so forth at a large scale, were always in situations where we had millions of these things correlated, and therefore the reality looked like it meant something to say that that was red or that was green or that, because we could check it all the time by looking at any other place. So it looked real. It only looks real because we have so many copies. But what we've discovered is that we can't make copies of more than one thing at a time, which is another way of saying making copies is a measurement, we could say, in a way. So we can't make copies of two that are correlated on two different lines is a statement. We can't make measurement of the two different quantities simultaneously. That's the uncertainty principle. Okay? I just want to compare making a measurement with these copies. You say, what has that got to do with it? What's the matter with pushing this button and looking at the light? Pushing the button and looking at the light really was making copies. Because a light, a real physical large bulb, puts photons out in all directions. You looking at the bulb can see it's red, and I'm standing over here, I can also see it's red, he can see it's red, he can see it's red, everybody can see it's red. That's an example of the correlation. It doesn't make any difference which box you look at, which photons, over there, or over there, or over there. They're always the same. That's this kind of correlation. So what we used to talk about crudely as pushing a button and reading and looking at a bulb was really a mechanism for making this type of correlated copy. Okay? That's the same thing. And the laws of interaction of matter permit us to make such copies, but do not permit us to make copies by which we can determine make a correlation that works both for the first button and the second button perfectly. We can make it perfect for the first button, but only 3/4 perfect for the second button. Now, mind you, there is a correlation in the second button. It just isn't perfect. The first button is all agree, but the second button, they don't all agree, but 3/4 of it, is more likely to agree than not. Okay? That's what I meant. It's more likely to agree with each other than not. Yeah, I said it right.
It's a beautiful model for me.
Yeah, it's getting better, right? Good, we're getting somewhere.
Now, if you had an observer that had a very peculiar visual system in which, when it showed red, he would sometimes see green.
Yes? Okay. Oh, sometimes. But then, let's say I have a... Oh, then this fella wouldn't be so hot at making observations of the world. He would be drunk most of the time.
No, but then he would...
I mean, it's like asking for a drunk observer. He doesn't make...
No, then he would correspond to box number 2.
Oh, so
He would make number 1 into a number 2.
But he'd make number 2 into something totally different.
He couldn't observe number 2 because his 3/4 probability.
Exactly.
And you wind up with you don't.
Yeah, whenever he observed, he's not very well correlated with...
Right.
He's only partly correlated.
Right.
There are observers like that, yes.
Yes, there are.
In fact, in certain...
Especially when they have LSD in.
Yes, but also in a certain sense, we are observers like that, because we can only amplify certain aspects of small things. This is an example. And so we are sort of seeing crudely, right? Right. Seeing crudely. And so one way of looking at the uncertainty in the world is to try to suppose that that these things are there, but we only see them crudely. This idea we have to get rid of. It doesn't work, because the whole discussion of this pair of boxes was this idea that there are red, green, and green, or green, red, red already, but we can't make it out very well. When we push buttons, it changes, it screws up. And that doesn't work, that's not enough. The world is still worse. We can't really understand the quantum mechanics by saying, there are all these things. It's either one, it's red, green, and green, or whatever combination. We just don't know what it is. And look, we don't see too well. That doesn't quite work because of this business of correlating these boxes as demonstrated, or the Einstein-Podolsky-Rosen paradox demonstrates. So the early ideas, if anybody first had them, that there were these things like position and momentum, but you couldn't just quite make them out simultaneously. It's not enough to understand the character of quantum mechanics. You can't say that there's both a position and a momentum simultaneously and be logically consistent in your predictions after that, after you've made that assumption, and use normal logic with what we observe. So we have learned not to say things like a particle has to have a position, have some position, I don't know what it is, but some position and momentum at the same time. That statement starts out by making an assumption, which sounds perfectly reasonable, because I can measure the position, or I can measure the momentum, but I can't measure both at the same time. But to suggest, therefore, that even though I can measure one or the other, that they're both possible there is a thing that we don't say now, and then we can use normal logic and get away with it without falling on our face too much, okay? Or at all, in fact.
You're not allowed an and, you just have an either or.
No, we're not even allowed an either. Oh, in a certain sense, it depends. Yes, we can't. It isn't quite an either or because there are other combinations. It's a little more subtle. And I'll try to explain the subtlety in the next lectures. But I believe that we are really all here together in appreciating, and I think it's marvelous that we can understand this, that we appreciate this reasonably. It's quite good. Thank you.
Okay, if you're obeying this rule,
Yes.
statement which says that you're not allowed to make certain statements and believe them anyway.
Right.
Okay. What does you made a statement earlier which sounded to me like you were making exactly that same statement. You said
No doubt, because I often slip.
that
As do most people.
particles don't have to be identical, but they have to have three states. Okay, what does it mean to say that particles have three states?
What I meant was that these boxes don't have to be identical. But each box has to have three buttons, three things that I can measure so I can talk about the correlations in order to be boxes that I'm interested in for this discussion here. That's all I meant. Nothing very deep at all.
In other words, when
all
you
I
say
said is that...
has three states,
No, I never went to say...
the states are carried
I didn't
out
mean...
by the particles.
No, I didn't mean to say anything about particles having three states, and I doubt if I ever said that, because in fact, this is not the way we describe that, so I probably didn't say that.
I wrote it down as soon as you said it.
All right, then in that case, I was trying to get an example of a situation that we're not supposed to say. That the particle's either in this, or this condition, or whatever. And I didn't mean that. What I meant when you asked me about identical particles or identical boxes was merely this. That all I really needed for this discussion was not that this box be exactly the same as this box. It could be a triangular box or something else, and the particles that went in them might have been different, but they're correlated. And in each one, you can measure one of three things with these boxes. And they give these results that are correlated together perfectly with three different button pushings.
Well, okay.
That's what I meant.
Well,
That's
it's not-
correct anyway,
it's not
whatever.
the threeness I'm quibbling with. It's the having what I'm quibbling with. Can we say a particle has a state?
We can say particles have states, yes, and we do say that. But in a new way, a way which I'll explain later on. In this particular example, believe it or not, this is done with a particle which has two states. So it's therefore not the kind of thing I would say, okay, that it had three states. If I did say it, I made a mistake.
No. Yeah,
I mean, I made an error, and you're right in asking. I didn't mean to say that. So it's a mistake.
And the threeness here is in fact an attribute of the
experimental setup.
Yes, the threeness here was simply a particular choice. With a particle with two states, there are many different buttons that you could measure, many different things you could measure. The situation can be more complicated. And the probabilities, however, always have this horrifying aspect that they're impossible to explain by supposing this kind of a picture. And I've just taken 3 to make it easy for you so you don't have to deal with complicated numbers. Actually, there are other things I could have measured about this object, which would have interfered with the measurements here. It's as if I had 17 buttons and then give you a long talk about 17 buttons here, 17 buttons there. Right? The same particles, as a matter of fact, were given. I even gave it exactly the same pair. But the particular machinery for making measurements is more elaborate. There are 17 things you can try. Then it would be a story that would go something like this. If you measure any one of the 17 possibilities, okay, the left by left center possibility, and you make the same left by left center measurement over here, they always agree. If, on the other hand, you measure, let's say, number 11 here, and then check 12 over there, they would agree with a probability 0.79 or whatever, okay? And that's, you know, and with number 10, there would be another number, and so forth. And then measuring 12 changes the chances of, for number 11 to such and such, with the big complicated numbers and all kinds of stuff. But it's much easier to take the 3 cases with the one number, 3/4, which we always come back to explain the character. The character of the phenomenon occurs again and again, that these numbers that I would have to give you for the 17 case would have this property that are inexplicable by supposing you have cards with 17 different, with red and green faces, and there are 17 cards in there and so on, okay? But the number 3, therefore, is exactly what you said. Simply a choice made for exposition or pedagogical purposes to make the simplest possible example.
But isn't this true of all statements about states, that it's always really a statement about the preparation setup?
I don't know what you're saying.
Not the particle itself.
I don't know what you're saying. All I've ever said is what happened when you push buttons, or what I should have said. But since we're trying to discuss theoretical explanations of what happens when I push buttons, I may have some of the time said, let us suppose that it's in one of 3 conditions or whatever. But that was a way of thinking. Yes?
The possible ambiguity in here was we got to have 3 states, meaning we got to have 3 things to measure, or 3.
Oh, yes, we do have to have at least 3 things to measure in order to see a paradoxical situation.
No, I think that's how you use the word states in that case.
Oh, is that right? Oh.
I don't know.
Well, whatever. I'm sorry if I confused the thing.
Yes.
I'm not worried about that.
Okay. Well, maybe you're worried about something you already knew before you came here. If that's the case, we're not allowed to discuss it.
I think there's something that you'll probably clarify in
Yes.
what you're going to say later on.
Go on. So yes? Well, let me get a chance at it, and then if you're still unhappy, we'll be very happy to try to explain, okay?
So what's the big deal now about Bell's theory?
What do you mean, big deal? That we've told you the
It is a
deal.
big deal. He showed it. He showed it.
We showed you. Don't you think this is a big deal, these funny numbers?
I do think it's a big.
Okay, that's all the deal is.
That's the big deal.
That's the big deal. Bell's theorem is a contribution to that deal, which is to point out mathematically that it has to happen. People knew it had to happen before. All he did was demonstrate it. It is not a theorem that anybody considers of any particular importance in quantum mechanics. We who use quantum mechanics have been using it all the time. Pay not much attention to it. It's not an important theorem. It's simply a statement of something that we know is true, sort of a mathematical proof of it. Once you've seen this example, you know it's true, that you can get situations that you can't explain. All of this is a demonstration mathematically from the original equations that this can happen. But you know it can happen from this particular example. So it is not really a theorem that stands in a big deal in the middle of the subject and represents a big contribution that before we had Bell's theorem, there were things that we couldn't figure out, and after we have Bell's theorem, it was a new light. Not at all. It's just a mathematical statement of something, a more precise statement of something we all knew. Okay?
People are trying to test this. Are there tests going on, as I understand?
We're always trying to test whether some of these predictions of the quantum mechanics that seem paradoxical from the point of view of classical thought, or these making this assumption that a thing has to be this way or that way before you look at it, that if they want to not break down that and think that maybe some of the things that are predicted by quantum mechanics are false. And so every time we take an example and discuss it, and they don't like that example, they think it can't happen, it's too crazy, then they insist that somebody, ask somebody to check it, or they try to check it. But none of these things have ever failed to work as expected. I really do believe that the quantum mechanics is fundamentally correct, and that all this is simply a psychological trouble that we have. It is extremely difficult to get used to it because it's so much common sense and common knowledge that gets this idea that when you're not looking at something, it's either this way or that way. And to be able to say that, my God, you can't even say it's either this way or that way when you don't look at it, but hey, it must be either this way or no, if you say that, you're going to get in trouble. They say that can't be so bad. There must be that nature isn't quite like that. And every hope that they have is one by one so far demolished, okay?
Well,
Whether they can find a way of doing it some other way, I don't know, but that's the way it is at the present moment.
Well, I understand that some people think about Bell's theory who philosophically or they believe that the universe is somehow connected. They try to use this idea that there's this connection between these processes, which is equivalent to Bell theorem, to say that indeed there is an instantaneous connection between things in the universe.
Yes, well, they would like to do it that way.
Yeah.
I must say to you that because this is unfamiliar, that there do appear all the time when you're thinking about things, difficulties that you're not satisfied with. And I'll try to explain some of those further on when we talk. The difficulties if we try to apply this idea somehow to the whole universe or something like that. And you say, well, we're in the universe and we're pushing the button isn't something done externally, and how is it done inside when, if you can't talk about the condition that things are in, how can you talk about the condition that the universe is in? After all, we're in it. And things like that produce a certain amount of trouble which haven't been thought through very well and leave us with a very uncomfortable feeling that the story isn't finished.
could it be that by suspending, say, one law of logic, like A equals B, C, then A, if you just suspend that it would work?
Well, yes, that's more or less what we do, but we suspend an assumption. We suspend an assumption that we are able to say things like, this is in either this or that condition, when you haven't made any observation yet. And then we can continue to think straightforwardly, and it's the most efficient way of doing it as far as we know. There might be another way by suspending some particular rule of reasoning and keep the old assumptions, but I don't know a particular way. And I'm just used to the way everybody else does it, which is to change the statement. We have a different statement. I'll just make words which won't mean anything to most, but we're going to say things like, a particle has an amplitude to be in this condition or that condition and so on. Not a chance or a probability or a reality of being in this condition, but another quality. And we would work with these so-called amplitudes and tell you how to combine them. So in the end, from this reasoning, you can predict what the probabilities will be. But this system of reasoning works, but we don't understand it any deeper than that this is a system that can replace the old system, but that works. Well, I don't know what else to say about it. It's very discomforting because it's so easy, it's so hard to believe that a simple-minded idea like the chicken in the icebox, that you can't say either there's chicken in the icebox or there's not chicken in the icebox until you open the door and look at the chicken, that you can't even say that there are these two alternatives or you get into trouble, is a kind of shock. And the shock keeps coming back. And no doubt, because we're all human, we're always sort of falling every once in a while. And I may well have said something about states or something was incorrect, because you sometimes fall off the wagon when trying to reason. But I'll show you the kind of reasoning that is done, the type of assumption that is made, and the system for computing the probabilities. But you'll be very dissatisfied by all that, because it all looks so crazy and abstract and mathematical and dopey, and you don't know why it works. And you say, well, wait, why? Same question. Why is it going to be this? We can't answer.
Well, I mean,
But I can tell you what the machinery is that we do use to figure out the probabilities. But the machinery wouldn't help to understand this.
I mean, there could very well be that there is a complex world you're entering, in which the common ways just don't work anymore.
That's what we think it is, actually. That's what I think it is.
Is part of the differentiation between the macro world and micro world that, for instance, there are chickens or not chickens in the icebox, which is a different thing then the probabilistic nature is what I'm getting a feeling about atomic phenomena.
Well, strictly, it's like this. When a thing is as big as a chicken or an icebox, since I could find out what's in the icebox by tapping it, by listening to the vibrations, by weighing the icebox and so on, there's all a situation that's so large. A chicken is so many atoms, it's so big, and it's light shining off it, so it's like this bulb, which is emitting photons in all directions. It's already made billions of copies of certain information, whether it's in or it's not. So that idea that we can't tell for a chicken is really an extreme. It's like saying, after I made thousands of these copies, I can't say that this is either red or green. What kind of a nervous, why are you so nervous? I could tell by looking at any one box. It's okay, but in a very delicate situation where I only have 2 boxes and I haven't amplified it yet, I can't say. So it's before you amplify information that you have to be careful. And you say it's the micro world. It's strictly, yes, it's the micro world, but the macro world we understand as being made out of micros. And so it's technically true of the larger world, but it's harder to get the situation because you have to be very delicate. In other words, yeah.
So
That's,
it's not because of the probabilistic nature, let's just say of nature playing dice or however you want to call it, that actually exists in a sense, if one's allowed to actually exist in that thing. In other words, I no longer have a need to say that nature has, it's free in this box. I mean, all of them in this box or that box, but I can see 3, 4 kind of probabilities happening. It just feels okay at that level in a certain sense to
when you,
see it as a probability rather than, as a 1 or 0.
it's not just probability. It isn't just probability that gives us our difficulty. We've discussed probability earlier, and there's a probability in classical physics if you don't know the details well enough.